Hey everyone, welcome back. We're starting a new chapter today, so let's get to it, and we're going to start off with this definition here. A function f of x is 1 to 1, which I usually abbreviate as 1-1, if f of x1 is not equal to f of x2 whenever x1 is not equal to x2. So what this is saying is that a function's 1 to 1 if distinct inputs always give distinct outputs. Distinct inputs give distinct outputs. You've probably seen this definition before, and you probably learned a way to identify graphs that are 1 to 1 or that correspond to 1 to 1 functions, right? And that's the horizontal line test. And here's the idea. If you have a function that's not 1 to 1, say something like that, then what you'll get, right, if there's a horizontal line that meets the graph more than one time, then what that gives you, for example, right here, there's an x1, and here's an x2. There's actually more than that, but for this setting, what we have is this spot and that spot right there. Both give us the same output. So here we have distinct inputs giving us the same output. Right? So here's an example of a graph that's not 1 to 1. Right? If at any spot you can draw a horizontal line that meets the graph more than one time, then you conclude that the function is not 1 to 1. So here's an example. Let's just give you an example. The function f of x equals x squared is not 1 to 1, and the reason, right, f of, let's say, -2 equals 4, which is equal to f of +2, right? So here what we have is distinct inputs give us the same output, not 1 to 1. Now, there's a reason that we like 1 to 1 functions, and this is it right here. So let's let f of x be 1 to 1 on its domain. So on its domain, let's call it capital A, and let B be the range of f of x, right? So we've got a 1 to 1 function. Let's call its domain capital A and call its range capital B. Now, so here's the reason we like 1 to 1 functions. It's because they have inverses. So the inverse of f of x is the function, move over here, so it's the function which we write f raised to the -1 of x with domain B and range capital A. So the first thing, the function and its inverse get the roles of domain and range reversed, right? And then we need to define it, so we need a formula for this. So it's defined by f inverse of x is equal to y if and only if f of y equals x. So there's the formula or the definition for the inverse function. And what it tells you is that the function and the inverse undo each other. If f of y equals x, so if f takes y and puts it in position x, then f inverse takes x and puts it back in its original position y. So if you think of a function as a sort of a machine that scrambles things up, then the inverse function just puts everything back to where it was. It undoes. Now, here's a warning, so make sure that you're aware of this. A warning. F inverse of x, that does not mean reciprocal. So the inverse function is not the same as 1 over f of x. So, so suppose, here's an example. Suppose f of x is 1 to 1, which means that the inverse function exists. And f of 3 equals 6, and f of 6 equals 3. Then, if we want to know, whoops, I wrote something wrong here. Sorry, f of 3, I want to equal 4, and f of 6 equal to 3. So then f inverse of 4 equals 3, right? They just reverse roles here. F inverse of 3, that's equal to 6. Now, here's our defining formula, our defining rule for the inverse function. But there's some equations that really capture the idea that the function and the inverse cancel each other out. So these are called the cancellation equations. And they go like this. So it tells us what happens when you do composition. F of f inverse of x, that's equal to x. Also, f inverse of f of x is equal to x, right? So if we have an inverse function, then the function and the inverse cancel each other out, right? They give us back x when you do that composition. Now, there's a couple of different ways to view the inverse function, and so let's label this finding inverses. So the first way, I want to think of it as graphically. So graphically, here's the relationship between a function and its inverse. If we have the function, let's say y equals f of x right here, let's do it like this. Then the inverse function, the graph of the inverse function, can be found by flipping about the line y equals x. And so, I probably got that a little lopsided. Let's do that better. So if I reflect about this line, something like that. So here's the graph y equals f inverse of x. Right? To find the graph of the inverse function, take the graph of the original function and reflect about the line y equals x. Now, I don't know, my phone is ringing. Hopefully that's not screwing anything up. Okay, so there's the graphic approach right there, and then there's also the algebraic approach. And I imagine that this is all review for you, that you learned this in pre-calculus at some point. But let's go over it. So the idea is to find it algebraically. So given y equals f of x, where our function is 1 to 1, first step, reverse the roles of x and y, so reverse x and y. And then the second step, solve for y to get y equals f inverse of x. So I imagine you've seen this before. Let's just do a quick example. So the example, let's say that we've got the function f of x equals x plus 1 divided by x. So x plus 1 all over x. You can check that this function actually is 1 to 1. So what I want to do is find the inverse. And so what I do is I write y equals x plus 1 over x. And then I reverse the roles of x and y. So that'll give me x equals y plus 1 over y. And now what I want to do is solve for y. Once I'm done, the formula that I'll have is the formula for the inverse function. So, okay, I'm going to multiply both sides by y. So we get y times x equals y plus 1. And then I'm going to subtract, so I get yx minus y equals 1. Then I can factor y out of each piece on the left-hand side. So that means y times x minus 1 equals 1. And so y equals 1 over x minus 1. That means then that we have the inverse function f inverse of x is 1 over x minus 1. Okay, so far we've been talking about inverse functions, but we haven't talked about the calculus of inverse functions. So that's what we want to look at now, is how calculus behaves when it comes to inverse functions. And so the first one, let's write this as a theorem. If f of x is 1 to 1, so that we know there is such a thing as an inverse, and continuous, then, and here I want to focus on the continuous part, right? So if I have a 1 to 1 function, and it's continuous, remember, what does continuous mean? That means that it has no holes or breaks in the graph. If my function has no holes, no breaks in the graph, and I reflect it about the line y equals x, right, that reflecting process is not going to introduce any holes or breaks in the graph also. And so that tells us then, if you start off with a continuous function that has an inverse, right, then the inverse will also be continuous. So we can say then f inverse of x is continuous. Right, so no surprise there. Now, here's what we want to do next, and let's ask this as a question, right? So if f of x is differentiable, is, and I guess I need to say 1 to 1, so and 1 to 1. Is the inverse function differentiable also? So let's think about what it means to be differentiable, and maybe a better way to say this, how does a function fail to be differentiable? There's 3 different ways to fail differentiability. The first way, having a sharp point, a cusp, right? So there's a point of non-differentiability anytime you have a sharp point. Another way to fail differentiability, right? A discontinuity, right? So functions at a point of discontinuity, the function is not differentiable. The third way is to have a vertical tangent. So thinking about the relationship graphically between a function and its inverse, right? If you start off with a function that's differentiable, that means that it has none of this stuff here. It doesn't have any sharp points, it doesn't have any breaks in the graph, and it doesn't have any vertical tangents. Can the inverse function end up being not differentiable? Well, if your original function doesn't have any cusps, then the reflected graph won't have any cusps. It won't have any breaks, but it could have a vertical tangent. If your original function has a horizontal tangent, then when you reflect it about the line y equals x, what you get is a vertical tangent. So the question is, well, it depends. I mean, sometimes the answer is yes, sometimes the answer is no. And so our computation actually is going to identify, well, if you don't have any of this stuff, you're good. But if you have a horizontal tangent, then the inverse function will fail to be differentiable at the corresponding point. Right, and so what we're going to do is we're actually going to find out a formula for the inverse function. So let's start with the cancellation equation. So from the cancellation equations, what we have is f inverse of x is equal to x. My goal is to find a formula for the inverse function. And so what I want to do is take the derivative of both sides. On the left-hand side, the derivative is going to be f, so I'm going to use the chain rule now, so f prime of f inverse of x times the derivative of the inside, which I'll write like this, f inverse x prime. Right, so there's the derivative of the left-hand side using the chain rule, and then the derivative on the other side, on the right-hand side, is the derivative of x is just 1. And so what that tells us is the derivative of the inverse function, let's put a prime here, is equal to 1 over f prime of f inverse of x. And this formula makes sense as long as we don't get 0 in the denominator. What would 0 in the denominator mean? It would mean f prime of some point is equal to 0. That would give us a horizontal tangent. So as long as we don't have a horizontal tangent at this spot right here, then the function is differentiable, and here's the formula for the derivative. So let me actually write this down. Like this, the derivative of f inverse of x is equal to 1 over f prime of f inverse of x, right? And this tells us everything we need to know about derivatives of inverse functions and their relationship to the original function. So let's try an example now. So let's look at the function f of x equals x to the 5th plus x cubed plus x, and what I want to do is find a formula. I want to find the derivative at a particular point. So let's find f inverse prime of 3. According to our formula, that's going to equal 1 over f prime of f inverse of 3. All I'm doing is putting a 3 where we see x. Okay, so the first step, our instructions are right here. First step is to remember our formula. It's the reciprocal of f prime of f inverse of 3. So the first thing I need to do, let's say step 1, I need to find f inverse of 3. To do that, I need to solve x to the 5th plus x cubed plus x equals 3. The solution, all right, we can just eyeball it. It's x equals 1. And so what that tells us is f inverse of 3 is equal to 1. All right? To find the inverse, set it equal to the number you're given and solve. So now I need to compute the derivative. So f prime of x, that's going to equal 5x to the 4th plus 3x squared plus 1. Now what do we need? We need f prime of f inverse of 3. So f prime of f inverse of 3 is equal to f prime of 1, which is equal to 5 plus 3 plus 1. That gives us 9. And so, final answer, f inverse prime of 3 is going to be the reciprocal of what we have there, so we get a 1/9. Okay, that's a good place to stop. We will see you next time.